Okay, let's get started. I'm honored to be the first class of the semester, so happy spring semester. Welcome back. We will start slow this morning. We will shake the rust off our brains and slowly spin up to talk about evolutionary robotics, which is why we're all here. So CS 206, Evolutionary Robotics. Today we're going to spend most of today talking about sort of the logistics of this class, how it works, what you can expect from myself and the TA, what we're going to expect from you, and hopefully at the end of today we'll be able to get into a little bit of the good stuff. Sound good? Okay, talking about logistics, this is a device-free zone between now and 9:45. I am going to use my device, but I'm going to need it to project the slides. We'll talk about that in a moment. Other housekeeping notes. I'm going to pass around a box of USB drives. Please take one and sign out the number that's on the USB drive, only if you're a Windows user. How many people here are Windows users? Okay, we have 40 USB drives. I think we have enough for everyone. So grab one, write the number on the sheet that's in the box, and I'll explain why you're doing that in a few minutes. There you go. Okay, so before we talk about logistics, let's just do a little bit of the fun stuff first. I'm going to show you your first evolved robot. You are going to see many of them throughout this course. The reason I'm showing you this particular robot is it was partly developed by a student that took this class 5 years ago. Nick Cheney grew up just down the road in Essex Junction, took this class 5 years ago. When he graduated from UVM, he went to go do a PhD at Cornell University. At Cornell, he was funded on a grant from NASA, and a particular NASA grant that was focused on trying to evolve a particular kind of robot known as a tensegrity robot. And this is a alpha prototype for a possible robot probe that NASA may consider sending to the outer moons of the solar system in the not too distant future, but we'll see. So let's just have a look at this robot first.
We're investigating how to
Let me play this first.
We're investigating how to use.
I'll narrate this robot as we go. This is the physical form of this robot. It was built at NASA Ames down in Silicon Valley, one of the research centers of NASA. Here is the same robot operating in a physics engine. You're going to be developing virtual robots in a physics engine in this
Today
class.
we're going to be looking at.
Anybody know what a tensegrity structure is? Forget tensegrity robots for a moment.
That is able to both land on a planetary surface, absorbing impact, and is also.
Tensegrity structures? Anybody have an idea? No? So tensegrity robots were, having some AV issues here, just bear with me.
We're investigating how to use these really novel tensile.
So tensegrity structures were originally developed in architecture to balance forces within a structure to make a very lightweight structure, but also something that can enclose humans or furniture or whatever you want to build your building around. That idea of tensegrity structures was recently adapted by a number of robotics groups into this idea of tensegrity robotics.
Soft, compliant, sort of more biological.
What are some of the advantages of this kind of robot compared to some of the other robots you might have seen in videos or maybe made yourself? Yep.
Well, it looks like it can sort of
thing can roll around the planetary surface.
Absolutely. So one of the things that keeps NASA engineers awake at night is what happens if we spend millions of taxpayer dollars and take 10 plus years to get a robot probe to Titan or wherever it is that it's going, and on landing, the robot comes in a little bit too hot, hits a little bit too hard, and something breaks. So one of the advantages of a tensegrity structure, which you can see here, imagine that we have some scientific payload in the center of the robot, and it's a very sensitive instrument. We want to make sure that that instrument experiences as gentle a landing as possible. We can build a tensegrity structure around it.
Surface, absorbing impact.
If you look carefully at this tensegrity structure, you'll notice you have a bunch of these rigid bars, and the tips of pairs of bars are attached with a spring, so that no two rigid bars are actually touching one another, which is what gives it its compliance, or this ability to bounce back and absorb sudden shocks.
And is also able
What might
to
be
move
another
around
advantage
and
of this
explore the
particular
planet.
kind of robot from NASA's perspective, aside from being able to cushion impact of a scientific instrument?
In space travel because your payload fairing volume is a premium.
Absolutely. So again, one of the major issues of anything that NASA sends into orbit is how much volume is it going to take up in the spacecraft that launches it up into orbit. If you take this tensegrity structure, pretty much any tensegrity structure, you can actually grasp it and it folds up into a one-dimensional bundle of sticks. So two advantages of these tensegrity robots. However, they have a disadvantage. What might the disadvantage be of this particular
What you see
device
here in the landing
compared to a
is
wheeled
the
rover, for
central
example?
payload, and it's that little sphere in the middle of all
Yep.
the rods. It's protected from.
It might be difficult to
impact
move
forces
around
of
in what
landing
sense?
By the elastic absorption of energy in this tensegrity structure. Much like we use
Absolutely,
our
right? So
muscles
the
to
wheeled
move our
rover
bodies
lands
around,
somewhere,
we are gonna be
telemetry
shortening
comes
and
up, mission
lengthening
control
the
says, all right, head
cables
for
of
that
these structures
crater
to
over
create
there. It's
motion
pretty
by
easy to figure out how to
changing
get the
the
wheeled
dynamic
robot to
balance
go over
tension in the
there,
system.
turn the wheels, and drive towards it. How would you actuate or how would you move this tensegrity structure? If you watch the little snippets of the physical robot, you'll notice that in the middle of these springs is a linear actuator. So an actuator is just a fancy name for a motor, and a linear actuator is basically a piston which can shorten the length of the spring or relax the spring. So it can actively pull these rigid rods together. Here you can see a tensegrity structure that has been actuated. So this robot can actually sense this little cube in its environment and will gradually walk towards it. It turns out that it's very anti-intuitive to figure out how to send commands to these linear actuators to push and pull on these springs to get it to move towards an object of interest.
Rubble and rocks.
So if it's so difficult to control this device, it's very difficult for a human engineer or a computer scientist to sit down and write a control program for it. So instead, what Nick helped NASA to do is to apply evolutionary robotics techniques to this. And basically what he did is create an evolutionary algorithm. I'm going to see what those look like. And that evolutionary algorithm would download a controller onto this robot, and the controller was just randomly pulling and pushing on these springs. In a simulation, the evolutionary algorithm would watch how well the tensegrity robot did at getting towards the target object and would assign a score to that particular controller that was pushing and pulling on the springs. It would then send another controller to the virtual robot, measure its quality, another, and another, and another, and another, and another. It would then delete the controllers that did a poor job of getting the robot towards the target object and would make randomly modified copies of the robots that did a little bit better job than the ones that were just deleted. Rinse and repeat. What I just described is an evolutionary robotics experiments. We're going to talk about dozens of them throughout the length of this course. But one of the advantages, as hopefully you can see in the simple example, is that if we have a robot that's difficult to control, we can use evolutionary robotics techniques. Okay, so as I mentioned, a former student helped out with this project. I don't expect that all of you are going to go work for NASA and help them develop their next generation of robot probes. Maybe you will. Some of you might end up in the robotics industry. Some of you might work in data science or machine learning. Whatever computational job you get after graduating from UVM, hopefully some of the material you'll see in this course comes in handy. So I said not all of you may work in the robotics industry. That's true. However, it's a very exciting time to be studying robotics. Machine learning, deep learning, AI, robotics, these are very popular topics at the moment. Just about 5 or 6 years ago, a lot of them were just purely academic studies, but now suddenly a lot of these algorithms have got to the point where they can be practically useful. And if they're practically useful, they're turning out to also be very profitable. So industry is becoming increasingly interested in machine learning, AI, and robotics. And there's a niche, I think, out there in industry for some of the robotics techniques we're going to talk about in this course. Okay, so that's just a teaser for some of the things that we're going to talk about in this class. Let's step back now and talk a little bit about logistics. I've now made the Blackboard page for CS206 available. Has anyone been able to access the Blackboard page? Okay, so it's up there. That's great. Okay, this is going to be the go-to page for everything in this course. So if you're not sure what we're doing at any given week or class, check out Blackboard. At the moment, I put up the syllabus and schedule, and we're going to walk through these two documents first. So you can find the syllabus here. Okay, so obviously we're in here Tuesday and Thursday mornings. I apologize if you're not a morning person. I am, but I will try and make things not just educational but entertaining. So I hope to see you here Tuesday and Thursday mornings. I hold 2 different office hours. The first one is going to be pretty much after this class in my office. My office is in Farrell Hall, which is on the old Trinity campus. Everybody know where the India House is on the corner there. The other side of the road, that's Trinity campus. You can find Farrell Hall back there. It's about a 10-minute walk. Maybe not so pleasant at this time of year, but it'll get easier as we go. I hold a second office hour on Tuesdays, 10 to 11:15. You can find me again in Farrell. The teaching assistant for this class is Rob Galloway. Rob, can you just stand up so everyone can see your face and know where to find you? Thanks very much, Rob. Rob will also be holding his office hours in Farrell Hall on Mondays and Tuesdays as well, but in the afternoon. Rob will be sitting at the desks in the second floor atrium of Farrell. So just come on over to Farrell, come up to the second floor, and you'll be able to find Rob. Okay, so I'm not going to read the course description. You can read this at your own leisure, but we're going to be talking in this course about autonomous machines. We're going to actually be talking about autonomous and adaptive machines. So an autonomous machine is a machine in which there is no human remote controlling it. And an adaptive machine is a machine that can somehow make decisions or change its behavior based on changes in its environment. As you're going to see in this course, it's relatively easy to make autonomous machines that are not adaptive, or to make adaptive machines that have a little bit of control, get some control from a human operator. So we can make adaptive but not quite autonomous machines. The open question in robotics as a whole is, how do we create autonomous and adaptive machines? There's a third adjective that's been added in just the last couple of years, which is also to make them safe. So if we have an adaptive machine that's making its own decisions in the real world, how do we make sure that those decisions concord with what humans would have liked the robot to have done? And we're going to talk about that third adjective, safety, towards the end of the course. So again, as we go along, keep that in mind. We're trying to make machines autonomous and also adaptive. Tricky thing to do. Students will conduct a major programming project that will span the course and give you some hands-on experience with robotics. The bulk of the work in this class is going to be Python programming. If your Python skills are a little bit rusty, I would suggest you take the time now at the beginning of the semester before things get busy to brush up on your Python skills. I sent around a link for an online Python tutorial. If you're rusty, work your way through there. Later in the course, we're going to be doing a lot of object-oriented programming. We're going to be making your Python code modular so that it will be easy for you to modify your code towards the end of the course when you're doing your own final project. If you're not comfortable with object-oriented programming in Python, there are lots of tutorials about that online. Go figure out how to do that. It will be very useful towards the second half of the course. Okay. Undergraduates in this course, you're going to spend the first 10 weeks doing some programming projects and then the last 4 weeks doing a final project. And I'm going to give you some ideas. If you have ideas of your own, we can talk about it. That's fine. Are there graduate students in this class? Hands up. 1, 2, 2 so far. Okay, so for the grad students, you are going to be going at twice the pace of the undergraduate students. So for every 1 assignment, you guys are going to be doing 2 a week, which will get you through all programming projects in the first 5 weeks, which will give you then 8 weeks to do a final project, and we'll talk about final projects when we get there. Sound good? Okay. As I mentioned, this is going to be a device-free zone. This is the first time that I've taught a course like this. It might be a little bit uncomfortable for those of you that have not taken a device-free course before. There's mounting evidence that there's a good reason to do this. You can go have a look at those papers if you like. As I mentioned in the email that I sent around to all of you, best thing to do is to print out the lecture slides, bring them to class, and annotate them as you go. If you're not comfortable doing that, pen and paper is also fine. I record all of the lectures and I'll put them online after class. So the other option is to watch the lecture again later today and annotate the slides on your devices at your leisure offline. Sound good? Okay. Okay, all lecture notes are available here on the schedule, and we'll work our way through the I'll come back to the schedule in a moment. All lecture notes are available here. As I mentioned, 2 options: print them out, annotate them by hand. You can print out the whole deck, which is now available as well. I think I have not yet put a link to the entire slide deck on Blackboard. I'll do that later today. You can also print out the individual slide decks as we go, and the individual slide decks are available as we go. So I've linked the slide deck for lecture 1. I'll put a link for lecture 2 later today, and it'll be ready to go for Thursday, and so on. So I'll gradually link up this schedule as we go. Okay, there is no required textbook for this class. The optional textbook is Floriano and Mattiusi. I will put a copy of it on loan in the library if you want to have a look at the book as a whole. I will put up PDFs of excerpts from the book as we go. And again, those excerpts will be linked from the schedule. So textbook is optional. Okay, there is a second optional textbook for this course. This was a book that I helped write a few years ago with Roel Pfeiffer, How the Body Shapes the Way We Think. Again, this is an optional textbook through the miracles of modern publishing. If you actually buy a copy of our book, I receive $1 for every copy sold. So if I convince all of you to buy a copy, I will make a grand total of $65. No real financial incentive here for me to get you to buy my book. If you do, I would be honored. Okay. So we will draw readings from these textbooks as we go. As we get later into the course, there's going to be additional readings that come from the current literature on evolutionary robotics. So the whole field of evolutionary robotics is about 25 years old. So it's still a very new field. It's not like calculus, which has been around for 300 years. There's a lot of flux going on in the field, a lot of new discoveries every year. So there's no real good evolutionary robotics textbook yet. Good news for you, that means textbook is optional. The challenge, however, is that as I mentioned later in the course, I'm going to be assigning some actual readings from the literature. For those of you that are not used to reading scientific literature firsthand, this will be a good experience to do so, and we'll talk about how to tackle research articles when we get there. Okay, as I mentioned, this is going to be a pretty Python programming heavy course, so I expect junior standing and programming experience. If you feel you're lacking one or both, please come see me during my office hours and we'll talk about whether this course is right for you. Okay, late policy. You're going to be handing in your assignments. 1 day late, 25% deduction. 2 days late, 50% deduction. And if you find that for some reason you have to submit something more than 2 days late, no need to submit it. Okay. As I mentioned, in the first 10 weeks of this course, for the undergraduates, you're going to be doing one programming project a week. These are cumulative, in which you're going to be adding code every week as you go. So do not fall behind. If you don't manage to finish one programming project 1 week, the next week you're going to have to finish it because the current one builds on top of it. So please, please, please make sure that you stay on top of the programming projects. Some of them are pretty short. The one for this week is pretty short. We'll talk about it in a few minutes' time. Might take you 15 minutes or 20 minutes. Some of them take much longer than 15 minutes or 20 minutes. I'll show you what they look like in a minute. They're broken into numbered steps. Some of them have 20 steps. Some of them have 100 steps. So you can sort of estimate the length of the programming project just by quickly scanning through it. I do not suggest you leave these programming projects for the night before. Okay. Quizzes. In addition to the programming assignments, you're going to be doing one quiz for every course day, every Tuesday and Thursday. So tonight there will be your first quiz due. It will be due at 11:59 p.m. tonight. So this evening you can go watch the video lecture. You can go read the reading for today. And if you came to lecture and you do the reading, the quiz should take you about 5 or 10 minutes, very quick. It's going to be on Blackboard, so when I get back to my office, I will post the quiz on Blackboard. You can take it any time between when I post it and 11:59 p.m. tonight. So the quizzes are just there as a prod to make sure that you keep up with the lecture material and the readings and so on. Not worth a lot, but again, a good idea to just keep taking them and stay on top of all of the material. Okay, over the final 4, or that should probably say 8 weeks of the semester, you're going to be doing your own programming project. So the first 10 programming projects are going to allow you to build up your own evolutionary robotics simulator, not unlike the simulator you just saw with the tensegrity robots. Once you have that simulator up and running, you can choose a final project. You can elaborate the structure of your robot. So I'm sorry, I forgot to mention, at the end of the 10 weeks, you're going to have a very simple robot operating in a very simple virtual environment. It's going to have a very simple controller. Remember, as the controller is the thing that allows the robot to react and behave in its environment. And you're going to have a very simple evolutionary algorithm, which is trying to improve that controller to get the robot to do something you want it to do in the environment. Simple robot, simple simulator, simple controller, simple evolutionary algorithm. For your final project, you can pick 1 or 2 of these 4 things and elaborate it. You might take the simple robot and turn it into a more complex robot, like the tensegrity robot that you saw here. You might take the simple robot and break it into multiple robots and evolve a robot swarm. You might make the controller inside the robot more sophisticated, so the robot is smarter than the one you ended up with at the end of 10 weeks. You might elaborate the evolutionary algorithm, the robot's environment, what you want it to do, and so on. We'll talk about it. Okay. Participation, I've definitely found that it helps if you come to class. So class participation counts for 5% towards your final grade. You can miss up to and including 3 classes. You don't need to tell me about it. If you find that you're missing more than 3 classes, come and let me know why, and I'm sure we can come to some arrangement. That should be fine. Okay. Why participation? Here's some data that you can digest at your leisure. Every dot here corresponds to one of the 102 students that have taken this class in the last 3 years. I've plotted their percent grade on the horizontal axis versus the number of classes that they missed. Generally speaking, students that tend to miss a number of classes tend to not do so well in this class. That's the data that I have. You make a decision about when and how often you want to come to class. Sound good? Okay. All right, so that's the syllabus. Any questions about course logistics so far? We're all good? Okay, so let's have a look at the schedule now. This is the other document that you want to refer to quite a bit. As I mentioned, as we go, I'm going to put up links to each of the individual slide decks as we go. After class, I will upload the video for today's lecture to YouTube, and then I will link it into the schedule as we go. I've done this 2 years in the past, so you can go and watch all lectures from last year if you like, for 2017 and the year before. As long as everything works with ScreenFlow, we should be fine, but sometimes something goes wrong, I miss a video lecture, or perhaps I go over a concept and you'd like to hear me explain it slightly differently. You can go back and look at previous year's lecture slides and watch them. So they're just there sort of as an archive for your reference. As I mentioned, I will also link all of the required reading for each class as we go. And over here, we'll keep track of all the assignments. So I've already put up assignment 1 for the undergraduates. You're going to be starting assignment 1 today, and it's going to be due a week from now, Monday night at 11:59 p.m. And we'll talk about that assignment in a moment. The reason I'm assigning you homework on the first day is for you to have a look at assignment number 1, see how well you do at coding up assignment 1. It's basically there's an opportunity for you to sort of figure out if this class is right for you. If you find assignment 1 to be a little bit challenging, this class might not be the right class for you. Okay. I've also linked assignment 2 because the grad students, you guys are going to be tackling assignments 1 and 2 this week. For the undergraduates, again, assignment 1 will be due next Monday night at 11:59 p.m. Okay, I've organized this course into 6 different themes. So again, we're going to go through a lot of material, but hopefully as we go, you'll see there's some underlying structure to this course. First 3 lectures are going to be sort of an introduction to this course. On Thursday, we're going to do a very, very short history of AI and robotics. We could do a whole course on that by now, but I'm just going to touch on some of the major concepts and challenges in the field and where we fit in. So evolutionary robotics is just one small branch of the study of robotics as a whole. So I'm going to try and situate where we are within the overall landscape of AI. We're going to talk about embodied cognition, which basically is the idea that the body plays a role in cognition or thinking. Embodied cognition is an idea that got started in psychology and philosophy and now has a lot to do with how we go about building robots. So we'll talk about embodied cognition as well. We'll then switch to the second theme of the course, the tools of the trade. There's lots of different moving pieces that go into an evolutionary robotics experiment. I've already mentioned the controller, the thing that gets the robot to behave. For most of the experiments we're going to see in this course, the controller takes the form of an artificial neural network. This is a very simple model of biological brains. Anybody take Professor Wishaw's machine learning class last semester? How about his deep learning class this semester? Couple people. Okay, so those 2 courses are sort of sister courses to this one. Professor Wishaw goes into a lot more detail about what these artificial neural networks are. We're going to go into just enough detail for you to know what they are and how to build them into your simulated robots. We're going to talk about evolutionary algorithms, the thing that searches for a robot and an artificial neural network to get your robot to do what you want it to do. We'll also talk about the physical simulation itself, how that works. We'll then do a history of evolutionary robotics. As I mentioned, this field's only been around for 25 years, so it's a pretty short history. We'll look at some of the initial experiments, this idea of minimal cognition. What is the simplest robot and the simplest neural network that we could put together to get the robot to do something that looks intelligent? That someone who doesn't know what's going on inside the robot, they might point to that robot and say, okay, it's getting a little bit smarter. We're going to spend a couple lectures talking about locomotion. One of the biggest challenges about getting robots to operate alongside people in the real world is getting those robots to move from point A to point B safely and efficiently. That's been a big challenge in robotics for a long time. We'll talk about that. By that point, we will all need a much-deserved break, spring recess, and we'll then move on to theme number 4, which are the open challenges in the field. Again, this is a young field, so a lot of the big questions have yet to be answered. We're going to look at a number of them. One of them is known somewhat tongue-in-cheek as crossing the reality gap. So we can evolve robots in simulation, like the tensegrity robot that you just saw. We then build a physical version of the tensegrity robot, and the physical robot doesn't act at all like its simulated counterpart does. Why? Why is it so difficult to get these evolved robots from simulation to reality? Usually they fail to cross the reality gap, and we'll talk about why that happens and some of the approaches to try and deal with that problem. We'll then talk a little bit about how do we scale these systems up. So instead of evolving just one simple robot to do one thing, could we create something like a production line where we can keep cranking out increasingly complex robots that are able to succeed at more and more tasks? We haven't been able to do that yet. What are some of the ways we might be able to attack that problem? We'll then have a 2-lecture discussion of collective or swarm robotics. So what tasks out there are better done by a large number of simple robots compared to one complicated robot? And once we find those tasks, how do we evolve a swarm of robots to actually perform that task? We'll then finish the course with the 6th and final theme, which is evolving bodies and brains. One of the things that distinguishes evolutionary robotics apart from all other branches of robotics is this use of an evolutionary algorithm. So rather than learning methods which tune up biological brains, or if we can adapt those learning methods to robots, tune up the neural network inside the robot, evolution doesn't just sculpt the brains of organisms or robots, it sculpts body and brain together. So we're going to spend a lot of time in this course looking at experiments where the evolutionary algorithm changes not just the controller of the robot, but the robot itself. And it turns out that's a more challenging thing to do, and we'll spend some time talking about different attempts to try and do so. Okay, that's the schedule. Any questions so far? So far, so good? Okay. Okay. So let's start with, now that we've covered the logistics, let's get into a little bit of what evolutionary robotics actually is. I've already mentioned this a few times now today, but just to really drive this point home, there are 4 basic ingredients to any evolutionary robotics experiment. If 30 years from now your elderly Professor Bongard emails you, or whatever exists 30 years from now, and asks you what are the 4 basic building blocks of an evolutionary robotics experiment, hopefully you remember this. If you forget everything else from the course, remember the 4 basic building blocks of an evolutionary robotics experiment. We need the task and what the robot is supposed to do, so its task environment. We need, obviously, the robot itself. We need the artificial neural network that's going to control the robot. As you'll see, artificial neural networks are basically transformers. They take sensory input that the robot is receiving, transform that sensory input in some way, maybe combine it with internal state or memory. The robot maybe remembers something and compares it to what it's seeing or sensing at the moment. And then the neural network sends commands to the robot's motors, and the robot starts to move. Finally, we have our evolutionary algorithm, which wraps around all these 3 pieces and is at heart a trial and error algorithm that attempts to find good neural networks, or maybe neural networks and bodies, if we're optimizing both, to get the robot to perform or succeed at the task in its environment. Okay, here's a sample experiment. This is taken from an evolutionary experiment that I did years ago. What you're going to see in this video is a snapshot of this evolutionary algorithm at work. In this experiment, the robot's body stayed constant, and the evolutionary algorithm was just making changes to the robot's brain. As I mentioned, evolutionary algorithms are basically a trial and error algorithm. So they try a bunch of things. Most of the things don't work, but every once in a while something works, and the evolutionary algorithm keeps that success, tries some more things, fail, fail, fail. Suddenly it makes a little bit more of an improvement, keeps that improvement, fail, 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 improvement, and so on. In this video, I'm showing you all the slight incremental improvements, and we're skipping over in this video all the many failures. What did I ask this robot to do? Pick up the blue object and not just pick it up, but put it on its quote-unquote back. Yes, we will anthropomorphize a lot as we go in this course. So I built in a fitness function, which is sort of the fifth component of an evolutionary robotics experiment. The fitness function allows the computer to score a given controller. How well did the robot do with that controller? The fitness function here is to minimize the distance between the blue object and this little gray sensor that you see on the robot's back. You can't see it in this simulation, but the blue object is actually a light source. It's emitting a light, and the sensor on its back is a light sensor. So it's basically trying to maximize the amount of light that falls on its sensor. That's the fitness function. Okay, so as I mentioned, what you're watching is a series of snapshots of this evolutionary algorithm in progress. What you're actually seeing in this video on the left is just the first phase of this experiment. Once the evolutionary algorithm finds a controller, finds a neural network that gets the object onto the robot's back, there's a threshold. So once the light sensor goes above some light threshold, we make a change now to the task environment. So in this next video, I'm going to really speed things up, which is I'm going to show you a bunch of snapshots of the robot succeeding, and every time it succeeds or light goes above this threshold, I'm going to make a change to the environment. So the very first clip, the first half a second in this video on the right, is the very last controller you saw in the video on the left. Make sense? So we're skipping over a whole bunch of controllers, and we're just going to see the one that got the light sensor above this light threshold. Every time that happens, I make a slight change to the task environment, and the evolutionary algorithm then continues trying to optimize controllers for that environment. What is the slight change that we're making to the environment?
You're moving the light source back.
Moving the light source back, right? So every time the robot succeeds, we make the task a little bit more difficult by moving the light source 1 millimeter further away from the robot. So the controller that worked just before, now maybe the robot fumbles the object, which means the fitness function scores that controller lower, and evolution has to sort of readapt the robot to the changed environment. So remember that in this course, we're trying to create autonomous and adaptive robots. This is an admittedly simple one, but it is both autonomous and adaptive. There's no grad student in the background remote controlling this virtual robot. It's autonomous, it's making its own decisions using its artificial neural network, and it's adapting as I make changes to the environment. Yes?
So how many iterations is like reasonable for like a successful one of these, I guess?
That's a very good question. So how many iterations, how many neural networks did the evolutionary algorithm have to try out until it started to get these successful ones? I think in this experiment, it was on the order of several million. So one of the challenges of evolutionary robotics, as you will definitely see when you start to code up your own evolutionary robotics experiment, is that this is extremely computationally intensive. This is a trial and error process. So for every one success, there may be 10 failures, 100 failures, 1,000 failures. Depends on what you've asked the robot to do. Yes.
So for each iteration, is the robot only able to, is the controller made so the robot's only able to succeed when the light is that far away, or can it do every single distance before as well?
That's a great question. So for every controller you're seeing here, is it evaluated against just that object placement, or can it also succeed at other object placements? In this simple experiment, it was only this object placement. We could take any one of the controllers that you're watching here and re-expose it to a different environment, and we could see how well it does. How robust is any one of these evolved solutions? That's another open challenge in the field. If we evolve the robot to do well in one or a few environments, how well will it do in 100 environments, or 1,000 environments, or 1,000,000 environments? Good question. What else can you tell me about what's going on during this evolutionary process? Aside from us trying out several million controllers, how well is the robot doing at this task? Was there anything surprising in its behavior?
When it was further away, when it was walking up to the blue light source,
Yes.
it was moving its arms kind of like upwards, and like it wasn't going to grab anything, but it was just doing that.
Exactly. So you'll notice that for a lot of these controllers, the pincers or the appendages move in phase with the legs. The reason why that tends to happen has to do with the artificial neural network. Remember that I mentioned an artificial neural network takes sensory information and passes it along to the motors, which cause the robot to move. And though that connection, all the connections tend to be interconnected. So whatever is happening to one subset of motors, like those in the legs, tend to also be happening in the arms. In this case, it's very difficult for evolution to come up with a modular solution where one module of the brain, or the ANN, controls the legs, and a separate independent module controls the arms. We're going to talk about modularity later in the course. Other observations from this video?
It seemed like not every change was actually an improvement.
Okay.
It seemed like it was actually pretty close at times, and then the success made it do something different, which actually made it a little worse.
Okay, so sometimes it does what looks to us like it's doing a little bit worse, like that, right? Picks up the object, falls onto its back, but doesn't hold on to the object. So there's a running joke in evolutionary robotics that evolved robots are very much like teenagers. They will do what you told them to do, which in this case was get the blue object close to the light sensor on its back, but usually will not do it in the way that you wanted it to do it in the first place, right? So it's meeting the letter of the law, the actual fitness function, but not the spirit of the law, right? Which was what I meant, which was grab, hold, and lift the object onto its back. This is an idea known as perverse instantiation. So the robot is instantiating in its neural network exactly what we wanted it, well, not exactly what we wanted it to do. It's instantiating a solution to the problem we asked it to solve, but it's doing it in a perverse manner. It's not quite what we had in mind. This is not just an academic question. This really matters. Imagine that you're writing control software for an autonomous car, and you ask it to drive safely. It instantiates safety, but maybe not in the way that you had actually meant. This is one of the big dangers, and one of the reasons why it's hard to make safe autonomous machines, is they often do exactly what we ask them to do, minimize the distance between the blue object and the light sensor, but they come up with a surprising solution which we don't like, or in this case, we weren't actually expecting. This is, again, a big open challenge in the field. Yep.
For this particular experiment, could you get what you want by saying you want it at max intensity for a period of time so it would hold it there?
Absolutely. So we could go back and change the fitness function, and we could say keep the light intensity above the threshold for a contiguous period of time, which it may be able to do. Is this new fitness function that we've just come up with, is it immune from perverse instantiation? What could possibly go wrong, right?
Just let go at the end.
It could go at the end, or it could lift it up, put it on its back, let go, and hold still, which is still probably not what we had in mind. It's often very difficult to craft a fitness function, which is our way of telling the robot what we want it to do. That's proof against perverse instantiation. Yes?
What's the benefit of designing a controller using like this method versus classical like control systems using system development?
That's it. So the advantage of this over classical control methods is, again, we're not going to, in most of the work that you're going to see in this course, we're not going to be just optimizing the controller. We're going to be optimizing the controller and the robot itself. So we're going to put more of the system, the robot, its sensors, its motors, its geometry, its material properties, which we'll get to when we talk about soft robotics. We're going to put all of those under the optimizer, which in our case is an evolutionary algorithm. And some of us in the field believe that this will ultimately lead to more safer robots than ones in which you're just optimizing the controller. But we'll get back to that topic later in the course. Yes?
In the course, will we, in terms of assessing the robot's performance, will we ever optimize any resources that might be used, or like battery life by robot?
That would be a perfect final project, right? So you could evolve robots to move, but move in an energy efficient manner. That sounds like a good final project. One other thing I'd like you to take away from this video on the right is you'll notice that the robot doesn't always move in exactly the same way. The evolutionary algorithm is continuously adapting one or a few neural networks, but with just small tweaks to the neural network, we get very different gaits or ways of moving. This is another advantage of evolutionary algorithms over classic control theory, is that evolutionary algorithms often give us a wide variety of solutions. Some of them we're not interested in for certain reasons. Others might be surprising and are even better than what we originally had in mind. So the spirit of evolutionary robotics is that we want to make as few assumptions about the robot as possible. We want it to solve a task, but we don't want to tell it how to solve it. We want to make as few assumptions as possible. Let evolution do what evolution does well, which is create lots of different kinds of solutions to problems. Okay. Oops. Okay, so just a little bit about who I am. I did my undergraduate in computer science in Canada at McMaster University. After my computer science degree, I went to work for a year at Computing Devices Canada, found that industry was not the right place for me, went back to school and did a master's in evolutionary and adaptive systems in the UK. The acronym for this course is the EASY course. It was definitely not an easy course. This MSc, which still exists, is interdisciplinary in that every year they take half computer scientists, engineers, and mathematicians, and the other half they take are biologists. The biologists have to take programming courses, and us poor computational people were thrown into wet labs and had to learn about biology the hard way. So this interdisciplinary approach to creating adaptive systems obviously is going to pervade this course. After doing my master's, I went to Switzerland and did a PhD at the University of Zurich with Rolf Pfeiffer. This is one of the few places at the time where you could pursue evolutionary robotics. After that, I spent 3 years at Cornell as a postdoc. I was also working on a NASA project, but a different NASA project, and we'll talk about that particular project later in the course. And I've been here at UVM ever since. Okay. So let's talk a little bit about expectations now, what I expect from you. Feedback, as you've already realized, this course lectures are a little bit interactive, so please feel free to ask questions, stop me and ask for clarification as we go. Common sense, regular but not perfect attendance, as I already mentioned. You're going to be doing a lot of coding in this class, so make sure you get a good start on all the programming projects. I expect memorization of key concepts. Obviously, all the quizzes are open book, as are the assignments, but hopefully, as you go, you'll start to absorb some of the core concepts. Why does that matter? Well, when you go look for a job and you're in a job interview, job interviews are closed book. You might mention in a job interview that you took a robotics course. They might say, great, tell me about that. What did you learn about in that course? If you can talk in some detail about some aspect of robotics, like neural networks, evolutionary algorithms, perverse instantiation, that'll usually go over pretty well in a job interview. So do your best as you're going to absorb the key concepts. We're going to see dozens and dozens of evolutionary robotics experiments. You've already seen 2. I don't expect you to memorize every detail of every experiment, but as we go, look for at least these 4 building blocks in each experiment. You'll usually see them. What was the environment? What did we ask the robot to do? What was the construction of the robot itself? Was it tensegrity? Was it legged? What was it that made that robot hard to control or easy to control? How was the robot controlled? What was the neural network inside? And a little bit about the particular evolutionary algorithm we used to optimize it. So look for sort of core concepts as we go. Okay, you'll have lots of opportunity for creativity. You get to come up with your own final project. Myself and the TA will work with you to make sure that your final project is both creative but also not overly ambitious. You'll only have 4 weeks at the end of the semester for that. We'll work with you on that. Self-learning. Again, Rob and myself are not here to teach you Python or object-oriented programming. Can't help you debug your code. This is an upper-level course. You should be able to figure those things out on your own. Positive attitude, I think, goes without saying. Okay, that's what you can expect from me. Me is in the royal me. This includes Rob and myself. As I just mentioned, we can't really help you with your buggy code. If you come in and tell Rob, why is my program crashing, he doesn't know either. Okay, presumably. Help with the programming language, installing software, and so on. This is sort of all up to you. Okay, what you can expect from us is help with specific programming questions. So in Python, you actually are going to be allocating and deallocating some variables as you go, and if you're not clear about why, Rob and I can explain that to you. Again, we expect you've tried to find answers to your questions online or from your peers as you go. I already mentioned in the introductory email, I think Codecademy is a great place to learn programming projects. It's all interactive, it's all browser-based, so away you go. I'm happy to help you with conceptual issues. Again, in this course, we're going to go over lots of different concepts as we go. If you'd like to talk about any one of them in more depth, please feel free to come to office hours and we can chat about them. Again, please make sure that you're clear about all the expectations for the projects as we go. If anything is unclear, please let me or Rob know. If it's something that the rest of you should know, we will broadcast the answer to that question back out on Blackboard. Okay. What you can also expect from me in this course is an emphasis on concepts rather than tools, because tools come and go, but concepts change much more slowly. When I started this course 5 years ago, we did everything in C++. Now we do everything, a couple of years ago we did half Python and half C++. Since last year, we now do everything in Python. If you come back and take this course in 5 years, we'll probably be using something completely differently. So I'm hoping that all of the tools that you see, the robots, the languages, the fitness functions, the physics engines, and so on, they help you to understand the core concepts as we go. Okay. All right, so that's enough about expectations, logistics, all good. We've still got a little bit of time, so let's talk a little bit about the assignments now. As I already mentioned, there are 10 of them. They're cumulative. What I'm going to do now is I'm going to walk you through the process about how to complete a project and then submit it to Blackboard. It turns out that there are 1, 2, 3, 4, 5, 6, 7 steps to do so. It looks like a lot of steps. Each one has a good reason, and I'm going to walk you through each of these 7 steps just so you've seen them. If you get confused as you're trying to submit your solution to a project, you can come back and watch the video lecture at this point. Okay, starting point is Blackboard, as we already saw. So if you go to Blackboard, course materials, there's a folder here of assignments, and in the assignments folder, you will already see assignment 1 and 2. If you click on the instructions, that will take you to Google Docs. And the Google Docs have instructions about assignment 1. So you're going from Blackboard to Google Docs. The reason why I describe the assignments in Google Docs is this course is also run online on Reddit. So starting today, there are a large number of online users that are also going to be taking the course alongside you. Obviously, they don't have access to Blackboard, but they're going to be jumping in at this point at Google Docs, and you're going to be working on these projects in parallel to the online students. Okay, so the Google Docs will explain what you're doing. They are misleadingly short because the actual details of the projects are in the online course itself, which is hosted on reddit.com. Everybody familiar with Reddit? You post links there. If everyone likes the links, they upvote it. If they don't like it, they downvote it. Okay. So when you click on the first assignment, it will take you to the course. It's the online course, which is again hosted here in Reddit. We have a subreddit which hosts the course called Ludobots. Why is the course called Ludobots? Anyone taken a course in Latin? What is Ludo? No? Ludo is to play. So here's where you can play with robots, make them, get them to do things, and so on. So from Google Docs, we come to the first assignment here. And as you can see, there are a number of numbered instructions here about how to complete the project. So step 1, click here, which will take you to a browser window. In this first project, you're not going to be actually doing any code, but just making your own robot in a web browser. So I'm going to connect the dots. This is the DotBot project. And when I connect the dots, I'm actually making the body of my robot. Now that I've made the body of my robot, when I click Go down here, I'm starting an evolutionary algorithm, which is going to optimize a controller for my robot. So in the DotBot project, humans make the bodies, and evolutionary algorithms make the brains. As you can see, this first random brain that the evolutionary algorithm has made is not doing a very good job, and the robot does not travel very far from the red dot, which is the origin. It traveled 2.84 centimeters from the origin. That's the fitness. If I clicked Go again, I give my evolutionary algorithm another chance to adapt the controller to this task. If I sat here and clicked Go dozens of times, hopefully we would see my particular robot gradually figuring out how to move further and further away from the origin. Yes?
Do you have, before you press Go like a whole bunch of times, you have to let it sort of practice and then give it some time and then press Go again?
Yes, you have to let it finish because it's evaluating just one controller or one neural network. At the end of that time, that number, 1.87, is how well that controller did. So I've clicked Go twice, which means there's 2 controllers. The first one was 2 point something. That controller produced an offspring, which was similar but not identical to the parent, and that offspring did slightly worse than the parent. Unfortunately, evolutionary algorithms are a little bit vicious. The child is going to be deleted, killed off, the parent will produce another child, and away we go. Okay, so I have now completed part of the first assignment. So if we go back to the instructions for a moment, towards the end here, it will say, take a screenshot and upload the screenshot. So let's go back to my project here. I won't rerun this robot just in the interest of time, but I'm going to take a screenshot of my robot, how well that robot did, and its fitness value, which again you can't see here because I haven't run it. I take a screenshot of my solution, which will now be saved here. And I go back to the Reddit. I go back to Reddit, and it's going to ask to upload the screenshot here. So we've now gone through Blackboard, we've gone to Google Docs, we've gone to Reddit, and I've done some code. Well, I will do some coding in the next project. I've done the work for this project. And I'm now going to upload a screenshot of my solution to Imager. You can drop it anywhere you want on the internet where you can store images. So let's drop my screenshot here. So I've now put my screenshot up on the web, and I get back a URL, which is over here. I'm going to copy that URL, so I now have a link that points to my solution. I'm now going to come back to Reddit. And at the end of this project, click on this here, Submit Work for this project. So I'm now submitting my solution on Reddit, and I'm submitting it to the Connect the Dotbot project here. And you'll see here in brackets it says Work Submission Details URLs here. So I'm going to drop the URL that points to my solution on Imager here. And I'm now going to submit my solution. Okay. So if we go back to the subreddit now, you'll notice that, hopefully it will show up here in a moment. Okay. It'll show up at the top here because it's the most recent submission. You can see actually in the last couple hours, a couple of online students have already submitted their solution to Connect the Dotbot. So if we click on any of these users' submissions, we can see there's a link in there to Imager, and we can actually see their solution on Imager. So in this course, you're not going to be submitting code as a submission for the project. You're submitting screenshots, and later in the course, you're going to be submitting videos. And we're going to diagnose from your images and video whether you got the project right or not. You will also be using the images and video to debug your code and make sure that everything is working. Okay. Okay, so now that we've submitted our assignment on Reddit, in some cases there's more than one Reddit assignment, so we might have to go back to the Google Docs. So please complete the first assignment here. I've done that. I've recorded the URL of my Reddit submission. So here's my, let's see, has it shown up yet? There it is. Okay, so Dr. Josh has submitted a solution. I click on here, and I now have a Reddit URL. So again, this is a little bit indirect. I have a Reddit URL that points to my Imager solution. And if I go back here, Reddit tells me to then go back to Google Docs, and I move on to the next assignment. So in this assignment, there's actually two sub-assignments. The first one is Connect the Dotbot. You end up producing the screenshot, and you're going to be submitting that link. The second one is going to involve Pyro Sim, which is a Python robot simulator. This is the virtual environment in which you're going to be building your robot. When you complete this second sub-assignment, you're going to see the following, which is just an empty virtual world. So this is Pyro Sim running on my machine now. At the moment, there is nothing inside here except some pretty clouds. I haven't built my robot in there yet. So what you're going to be showing us in this second sub-assignment is that you're able to install and get the empty Pyro Sim simulator up and running. Pretty straightforward. Okay. So let's talk about Pyro Sim installation for a moment. Pyro Sim is some software we developed in my research lab. It works perfectly for Mac. It works perfectly for Linux. It does not yet work well for Windows. We have a large number of Windows users in the audience today. So that's what the USB drive is for. So for all the Windows users, you'll see there's instructions in this second sub-assignment here. Maybe it's worth going through here. So now in the second sub-assignment, I've moved on from the Connect the Dotbot project to the simulator. And here are the installation instructions. The USB drive is actually a persistent drive. So what that means is on your Windows machine, when you plug in the USB drive and you reboot your computer, it's not going to come up in Windows, it's going to come up in Linux. Again, I apologize that we don't have this working on Windows yet. So all of you that are Windows users, you're going to be working on Pyro Sim in Linux. When you finish working on your assignment, shut down your machine, pull out the USB drive, turn your computer back on, and it'll reboot up into Windows. It's not the most elegant solution, but it's the best we could come up with. One other point about the USB drive is when you boot up in Linux on the USB drive, you do not have access to the internet. Again, I apologize for that, but maybe it will help you concentrate on finishing your Pyro Sim project. Any questions about that? So those of you that are on Mac and Linux, there are a few steps to install it on your machine. Windows users, you don't have to install anything. You're just plugging in the USB drive, and when you boot up your machine, Pyro Sim and everything you need will be there. Okay, I think that's it about installation. So let's go back to Imager, Reddit, Google Docs question.
So what exactly is Pyro Sim? Is that the thing that runs your robot? Like when do we write code?
Okay.
Does that have to be
Okay, so that's a good question. So again, when you finish the first project, this is the Python code that you're going to be writing. You're going to be importing Pyro Sim. So Pyro Sim is a Python package which will give you access to the simulator and all the robot bits and pieces you're going to be assembling. This line creates an instance of the simulator. It creates that window that opens up. The argument there tells the simulation to start in paused mode. We can unpause it later, you'll see that. This line starts the simulation running. When you start to build the robot, you're going to be putting an increasing number of lines between these two lines. You're going to be sending body parts that make up the robot. You're going to be sending joints which connect pairs of objects together. You're going to be sending sensors. You're going to be sending motors. You're going to be sending parts of the artificial neural network. You're going to be constructing your robot like Lego in the simulator. Once the robot is constructed, you hit start and the robot will be simulated in the simulator. When the robot finishes doing whatever it does, you've been waiting for it to finish. You'll be adding a line after this which grabs all the sensor data back from the robot. So this code here is a minimal single simulation that runs through the simulation of a robot, the moment it's a null robot. Later in the course, you're going to be wrapping these lines in an evolutionary algorithm that's going to loop hundreds or thousands, or if you have a fast enough machine, millions of times through this. Simulate this robot, this robot, this robot, this robot, this robot, and so on. Make sense? Okay. Okay, back to submission. So let's imagine now that I've finished this Pyro Sim sub-assignment and I've submitted it to Reddit. So I have one Reddit submission, which is my screenshot of the dotbot. And I also have a second Reddit submission, which is my pointer to a screenshot of my empty simulator. I've got dotbot and empty simulator, so I have two Reddit URLs. The last step is to go back to Blackboard and go back to Blackboard and find assignment 1. I'm now ready to submit to assignment 1. I go down here to the comments and I copy and paste those two Reddit URLs. One that points to the dotbot and the other that points to Pyro Sim. And that's what Rob is going to see when he grades your assignments. Sound good? Oops. Got too many windows open here. Okay, so I apologize, it's a little bit of an involved process, but again, the reason why is so that these online students can take the course alongside you. They obviously don't have access to Blackboard, so they can submit their assignments, but they're not being graded. What I would ask you to do as good fellow students is to actually, once you've finished assignment 1, have a look at some of the other submissions and have a look at those screenshots. It might be that in some of those screenshots the students didn't quite get something right, and you might see that error in the screenshot. Rather than downvoting their submission, I'd ask you to add a comment and act as a good TA, give them some suggestions. So you might, for example, see in later assignments that they submitted their robot and the robot's leg is at 60 degrees and it should have been at 90 degrees. You might see that in the screenshot, and you might mention that they go look in their code at where they set the joint that connects pairs of objects together. That'll be more clear when we get further into the class, but again, try not to downvote your fellow students' submissions, but posting comments and helping them try and find the errors in their code is perfectly acceptable and encouraged. Yes?
How many random online students do you have?
Good question. Last year we had about 100, 150. We'll see how we do this year. Who knows? Okay. Obviously they're just taking it for fun, so we might see a lot this week, many fewer next week, and we'll see how we do. Okay, again, I apologize, it's this long, involved process, but hopefully you'll figure it out as we go. Okay, we've got 5 minutes left, so let's just talk about the final project. As I mentioned, you're going to be doing these 10 weekly programming projects. When you get to the final 4 weeks, you can come up with your own ideas. We will also give you some ideas that have worked in the past. We're going to talk about lots of evolutionary robotics experiments. If there's something cool that you find interesting, you might note that down as a possible seed idea for the final project. Here are some projects that have been done in the past. I'll also put up some videos from these projects so you can sort of see them visually. Given the same optimizer or the same evolutionary algorithm neural network and 8 hours of behavior optimization on the same computer, does a 4-legged robot evolve to walk further or not as far as a 6-legged robot, or is there no significant difference between this? So why 8 hours? Once you have your evolutionary robotics simulator up and going, as I mentioned, it takes quite a bit of computational effort. So hopefully in the last 4 weeks, you'll get in the rhythm of starting up your evolutionary algorithm in the evening and let it run for 8 hours. And when you get up in the morning over a cup of coffee, you can see whether your robot evolved to do what you wanted it to do, or it came up with a way of optimizing your fitness function in a way that you didn't want it to do. Basically, which is easier for an evolutionary algorithm to get to move? Is it easier to move a 4-legged robot or a 6-legged robot? Another project is you might change the fitness function. So instead of just selecting for fastest motion away from the origin, how would you create a fitness function that selects for a particular 4-legged gait? Walking, trotting, cantering, galloping, or pronking? Are there any horse people here? Okay. Yes, a little bit?
I've heard the term before. I know what it is.
Okay, all right. Well, we're going to spend a lot of time talking about 4-legged locomotion and 2-legged locomotion, which you're probably more familiar with. How do we create a fitness function that selects for particular ways of moving? We could, for example, create a fitness function in project 3 here that penalizes for requiring a lot of energy. So we already mentioned this idea of energy efficiency. That would be a great project to tackle. We could equip our robot with a laser rangefinder so that it can see objects in its environment, and we might evolve robots to move towards round objects and away from rectangular objects. Categorizing objects in the real world, friend from foe, food from poison, dangerous from safe situations. Obviously, these are one of the building blocks of intelligence. That might be a good thing to tackle in a final project as well. Okay, that's the end of all the logistics. I think we'll pause here, and next on Thursday we'll talk about why we might want to build robots in the first place. 2 reminders. You have a quiz due at 11:59 p.m. tonight. If you're a Windows user, make sure you've signed out a USB key. And your first project is due Monday night, 11:59 p.m. See you Thursday.